The solution for exercise 3 is out on the home page, but it's done a little special. You will find a PDF file for sort of the entire case, and also you'll find a zip file containing the source code and other files as well. And I will explain why. Here is a standard MATLAB script, but I have used some double percentages, some strange syntax here, yada yada yada, and also here %* and so on, which then gives you a possibility here to generate a PDF file, a report directly. I'll show you. First of all, using this percentage signs, you will change sort of the logic here. The code will be split up into blocks, and actually it's possible here to execute just one block if you like. That's actually an option. Here, if I now run the entire code, it then should work. Hopefully. So here, the first attempt here. Now I have positive direction upwards. So when the guy jumps on the bike, you see this oscillating motion, and then it levels off, as it should. And then you have to press a key to continue the program. I just use a pause command in MATLAB. And now he starts to bike over sinusoidal ground. And here the frequency is very low, meaning he doesn't hardly care about them. He just follows the ground perfectly. So the waves are very, very, very long. If the waves are shorter, then you start getting, you fly a little bit up and you go a little bit down in the valleys. And when you hit your eigen frequency, then of course the system breaks down. It explodes. Here the damper is not strong enough to handle it, so it will really break. Twice as fast and 10 times as fast. Now the ground is very rapid. I mean, the noise from the ground is very, very high frequent, very bumpy. So when you bicycle over the small bumps, very small, very close, you'll only feel it when you're biking. So you hardly ever move, just a little bit shaking. So as you can see from the blue one there. Final simulation, you bike down a step. So here I imagine the following. I have a step, something like this. And here you come with your wheel, and you move in this direction. So what happens? Well, mathematically, it's sort of impossible to describe this because we want the velocity, not the displacement. And the velocity goes to infinity when you do something like this. So I just imagine this has already happened. And he went here and then passed the step. And sort of the wheel is glued to the ground, and all of a sudden the wheel is all of a sudden down here. And then I start the clock. I start the simulation at time equals 0, meaning this has already happened. So the wheel is here, and sort of the spring is stretched very, very much. And then you also see what happens. Of course, he falls down, and he falls down roughly 50% deeper than the step. Okay, that was the simulation. It's a little bit printout. But now you have an interesting button here. It's called Publish. So that's where you now can generate a report. When you do this, the first thing you have to do is to set or edit these options, because default is going to be a web page, HTML, which is you're not interested in. So click on this HTML, and choose PDF. Here actually you can choose doc if you want to have a Word file, which you can edit afterwards. That's also an option. Here I want to just do it crudely, PDF. And then I just click on publish, see what happens. So what he now does is he tries to run the entire code again while generating a PDF file. So let's see. I still have to do this, press any key to continue, since I used the pause. So I have to step through the entire code. And now he should then generate this PDF file if everything works okay, and he should display it. Yeah, I guess I have to accept something here. Yeah. Here we go. So this would now be my report, actually with a table of contents and everything. Here, it's just a handwritten piece of paper that I scanned as a JPEG file. He can load it into the report. And he will display the source code with comments, and then the printout as the code runs. So it's actually quite convenient way to generate a report. So this is really something you should have a peek into. And finally, here I also included the function file. So if you have a look at the source code, you can see how this is done. Now, if you want to start playing around with this, you will have one experience, the same as I had, I guess. You now change something in the code, and then you want to publish again. So you just hit another publish, and then you have to run through the entire code again. Well, actually, I don't think you're allowed to here. No. So he says here, reasonably enough, it's not writable, meaning I haven't closed down this reader. The PDF file is open, so he can't make another one. You have to close this one first. Okay, then you're allowed to run another publish round. So just remember, shut down the PDF file. Okay, any questions to that one? Goodie. I've been playing around with this problem here to let's see, editor, open. I tried to make an animation out of it. I'll see if I can make it finished by tomorrow. Let's see if it works. Just to give you an idea of what's possible, quite simple actually in MATLAB. So here we have the mouse, and then he levels off after say a couple of seconds, and then he actually starts to move. So, but I haven't done all the programming yet. So yes, it's actually quite possible to program some animations here. So I come this far, and then I stopped. I'll see what I can do. So I'll put out the source code when I'm done with it, so you can have a look how this can be done. Let's see. You have been given exercise 4. So it's out. You have given a lot of different problems in all the 4 different energy domains. So your job is to pick one from each of the 4 different domains and do everything, meaning find the state equations, find the differential equations. Choose one problem, one of the D problems, and also create a MATLAB program and do the simulation. Then you have to invent some numbers for the different elements, but that should be possible. And the problems, as you can see, cute, small, little problems. Mechanical, rotational, electric systems, and fluid systems. So it should be very good training for dealing with bond graphs and finding the state equation. And the reason I yell at you that this is the equation, the exercise you have to do. This is the important one. Forget all the rest. This is the one you do. You really put in some work here. And why? Well, because I have some very, very nice solution to it. So if you look at, as an example, take the first one, problem 1a here, this mechanical system. So here, if we can make it run, this is actually made by a colleague of mine some years ago. He did it in Norwegian, sadly, so it's not in English. Furthermore, we had the exercise then was numbered 5 and not 4, but never mind that. So here you can now step through the entire problem, step by step. Here you have the physical problem, and then finding, as you know now with mechanical problems, identify the different objects, points with its own velocity. If they have mass, attach it. For the other, if you have a source, add it, yes. For the other elements, insert it with a 0 junction, and then close everything. And then you remove actually the problem, the physical problem. Now you are only in the bond graph world. So now start to simplify. Remove bonds with 0 power, remove junctions with only 2 bonds. And then we have the sort of clean bond graph. And now, starting with causal strokes. Start with the sources, and then you choose. Here we start with a C element, continuing. Then the 0 dictates a stroke towards the 1 junction. Okay, then we have to choose again. So now I choose an I element. Aha, then you have found the 1 stroke away from that 1 junction. Then the 2 others are given. And then start to annotate the graph. Here you have 3 elements with integral causal form, so it's a 3rd order system. And you instantly write up all the dots with a circle around, and on the other side also you now have Q over C as an effort, and Q over C as an effort for the other spring, and he's hooked up on a 0 junction, so then you know it's a common effort around him. And then you know the flow for the inertance, P over I. Well, he dictates the flow around that 1 junction, so you have P over I here. And then finally you're missing the force from the resistance, and done. And from that, now you should be able to find all the differential equations. Should be 3 of them. And you have it here. So with this system here, you can, I think it's done from PowerPoint actually. You can create an execute file. So here you can go back, previous, next slide, first slide, whatever, play around with it. Or also use page up, page down. And after the last one, well, he's just finished. So I have solution for all these 16 problems like that. So it's very nice afterwards when you have been fighting with it and you're wondering, is this correct or not? Then you have it really nice, step by step. So this is the exercise where you learn bond graph. So do this one. Forget about the rest. Okay, any questions to that one? It's okay?
Will you give us that thing, or simulation thing?
The simulation, what do you mean? These?
Like this,
Yeah. I have 16 of these execute files. So you will have all of them as a part of the solution. Maybe not so fun with those of you who has a Macintosh. These are execute files for Windows. So if you have a Macintosh, then throw it away and run and buy a Windows machine. Of course. Yeah?
It's possible to use wine.
Yeah. something like that. You can use some virtual environment for Windows. Other questions? No? We have a little bit time. We can do an example. Let's do a little example. We have the following problem. Solid wall, and we have a spring, and then we have a wheel, and then we have a smaller wheel here, and he can rotate around this point. So here I have now a radius 1, and here I have radius number 2, like that. So this string is sort of winding up here, and on the inner cylinder you have another string winding up, and down here you have a mass M. This wheel also have inertance. I call that one J, rotational inertance. The spring stiffness, yes, we have a K up here, which then is of course 1 over C. We have the radiuses, then I think we have everything, and also of course the system is attacked by gravity. Find the bond graph, find the differential equations, find the state equations necessary to describe this system. Okay, so how do we deal with that one? It's not so trivial actually, but let's try. I start with a wheel. It's a massive wheel that sort of goes in either directions here. At least he has his own rotational speed. So he will have a 1 junction, and he has inertance attached to him. That's the J. So he will be hooked up directly there. Now from the wheel, if we go towards the spring, yes, we can do that, but I mean this wheel will rotate, while the motion for the spring, that will be purely translatoric. Hey, we need to go from one domain to another. How do we do that? Well, if you know the rotational speed of the wheel, then you can easily calculate what's the rotational speed here for this, this string moving back and forth. Well, they will be directly coupled, hence, yes, it must be a transformer. What do I call that one? T1. And from this transformer, now we are in the translatoric part. Here I have a spring, that one is inserted with a 0 up to a C element, and then finally I have a solid wall, x dot equals 0. Going the other way, from the rotational wheel down to this mass M, he will jump up and down. Again, translatoric motion. So then I'm going to need another transformer, T2, going like this and going like this, and down here I have a 1 junction which has mass attached to it. And also the final mass down here, he is attacked by gravity. So that's an effort source. So there we have sort of the raw bond graph. Let's have a look at these transformers. Let's take T1 first. T1. Now I have sort of the arrow moving to the left here, so let's continue with that, like this and like this. And I go sort of from the wheel through the transformer over to towards the spring here. So I start here. I have a rotational speed, a phi dot. What do you get on the other side? Well, what's the definition of a transformer? It actually goes the other way. So here the arrow direction is important. So here you have a flow 1. Down here you have a flow 2 equals to T multiplied with flow 1. So that should be the same, but I just go the other way around. But here I will now have a T1 multiplied with phi dot. That will be my velocity. That should be my x dot. Okay, from that, what is the value of the transformer T1? Well, quite clearly, he must then be equal to the radius R2. Rotational speed times radius gives you a velocity. So this one equals R2. Everybody with me on that one? Check the dimension if you're in doubt. Here, this one has the dimension radians per second. Radians has no one dimension actually, so it's only 1 over second. Multiplied with meters, meters per second. Aha, that's the velocity. Yes, this looks good. So check the dimension, that's a good trick. What about the other one? Well then, I turn my arrows. I go to the right there, finding T2 and going like that. Okay, again, I start with the rotational speed. And what do I have on the other side? Well, I have a velocity. So that must now be rotational speed multiplied with T2. Should be a velocity. What is then T number 2? Well, a bit the same as this one actually, but it will be radius number 1, the inner radius. Okay? Then we have the transformers. So now let's try to draw the entire bond graph. I start with the one junction in the center here. Now he has mass attached to him, so I put up the J up here. Then I go to the left. There I have the transformer number 1, and continuing, finding actually a 0 up to a spring C, and then continuing to the 1 junction with 0 velocity. But now you should be experienced enough to see, okay, he's 0. So I can just go straight to a C element. If you're in doubt, of course you can do it the long way, a 0 up to a C and then another 1 junction, and then simplify it afterwards. The result should be the same. Going the other way, then I have T2, and then we have, what do we have? I have a 1 junction all the way down here. This 1 junction has mass, and he is attacked by gravity, like that. So that should be the entire bond graph. And now we actually can do another simplification, if you can recall. Here we have a transformer and a spring. That's also a part of these possible equivalences. Yes, we can have an equivalent C marked to cover both of these. Here I don't bother, I just leave it as it is. So now let's try to annotate this one. and see how it goes. How do you think it will go? Will this be a causal system? Will it be an over-causal system, or will it be an under-causal system? Can you guess? An under-causal, to get an under-causal system, then you needed a lot of resistances. I don't have many resistances here, so no, it's not going to be an under-causal system. Over-causal, what was that? Well, that was one of the eyes, or the inertances of the spring, got the wrong stroke. You got a differential causal stroke. When does that happen? That will happen if you have some direct coupling here. And don't we have that here? If you know the rotation of the wheel, then you know the speed of the mass m going up and down. They are directly coupled. Clearly, this is going to be an over-causal system. Let's try. Start with the mass. Sorry, not the mass, the gravity. He's unquestionable like that. Okay, that doesn't dictate anything. So I choose, take the first mass up here and choose the correct integral form for him. Then this one junction dictates stroke has to be like that. The transformer dictates stroke has to be like that. This one junction dictates both these two strokes has to be towards him. Yes, and then you see the J got the wrong causal stroke. Continuing, transformer doesn't change anything. And finally the spring, well, he will be on the integral form. If you had chosen differently in the beginning, instead of choosing him, you could have chosen this one with the integral form. Then this one junction would have dictate stroke, stroke, and he would dictate a stroke, and then stroke here. Then it will still be an over-causal case. So one of these masses will give you a differential equation, the other one will not. Your choice which one. Doesn't really matter. So now let's try to annotate this bond graph. Here we have the gravity, mg, and the flow, I don't care. This I element is on the correct form, so I can write p dot circle, and on the other side, p over I. So here's a convenient. I have the mass m, that's I. The j, that's the rotational mass here. So the rotational inertia for the wheel. That's j, or else I have to use I1 and I2, but never mind. Okay, that was for the I element on the correct form. Now the C element is also on the correct form. So here instantly we can write q dot circle and q over c as an effort. That you can do instantly without thinking. Now we have to sort of start to nest up the entire bond graph. Let's start, where should you start? Well, a little bit training, then you know where to start, but without the training, well, you can just try. We only have two junctions, so let's try with this one then. Who dictates the common flow here? Well, that's where you're missing a stroke, so the flow here, I don't have him. Must be the flow here. Well, I don't have that one either, so no, bad idea to start with the one junction to the left. Start instead with the one junction to the right. Who dictates the flow? That's where you're missing a stroke. This is P over I thing. Then we have the flow here, P over I. Absolutely. And from the transformer here, when we know the P over I here, we sort of go backwards. What will it be? Going backwards. I have the flow here. What will then the flow be on the other side? That will now be 1 over T. So here should be P divided by T2 multiplied with I. Then I have the common flow around this one junction. Okay, then I know this one, the flow here, P divided by T2I. What will the effort be on the other side when you have an inertance with the wrong causal form? It's a differential form. That was tricky, wasn't it? Well, what was it? If it's the right one, you have P dot P over I. If you go the other way, you have something here for the flow. How to construct a P dot? Well, you multiply with an I, then he disappears, and then you take the derivative. So here you will have d dt of this one, P over T2I multiplied with him. There you have the effort for this for the wheel. Okay. Continuing around this one junction, we know the flow, and we also know the flow here, P, and then we have a T2 and an I element. Now here is a little tricky thing here. This flow has to come on the other side, but there we have a Q dot. So this is not so easy to see what Q dot then equals. Remember, we go through a transformer also, so it's sort of two steps in one. So maybe if you want, you could do it like this. Easier to see. One, and then a C element. You add an additional one element, one junction. It doesn't do anything sensible. I mean, it's the same flow on each side, but it's easier to see because now here you can write P divided by, now you go the right way through a transformer. This one, go the right way, you have the flow here, then what will the flow be on the other side? That will be multiplied with T1, and under we had T2 and the I element. Then you have sort of a nice expression for the flow here. And that one equals Q dot. And then Q over C on the other side. Easier to see the first equation there. Q dot equals P I1 divided by I2 and T2 and I. So that was the first equation. The sum of effort has to be the same, so of course Q of C has to be on both of them. And then going through a transformer, what do we find here on the other side? That will now be multiplied with T1, Q over C. Then you have the effort here. Okay, what are we missing? We are missing an effort here and an effort here. And now you see I'm running out of space. So let's invent a variable A here. What will this A variable be? What's this effort here? Well, here I now have to use the summation rule around this one junction. I'm finding the effort that goes out from the one junction equals what comes in, and nothing comes in, everything goes out. Hence this A has to be equal to minus T1 Q over C minus, and then this time derivative of this bracket. Having found an expression for A, you can find an expression for what's here on the other side. Well, that must now be A multiplied with 1 over T2. And then finally, summation rule around the last one junction to find an equation for P dot. Sum of the effort around this one has to be 0, so what goes out, P dot, equals what comes in. gravity, and then this A1 over T2. There you have it. Any questions to that one? Yep.
When you inserted that one junction to help you out there,
yeah.
do you have to worry about the constant stroke or anything like that?
Yeah, well, he doesn't change the strokes, so it will be the same. So the reason I did it is just that I had a flow here and then through a transformer hitting a Q dot. So it's a little messy to have both these operations in one. So typically here the T1 will disappear if you're not careful. So that's why I inserted that one junction, just to help me see it. But you don't have to do it if you don't need to. Your choice. When you're given a task in actually any course, say on an exam for instance, students, they all do the same mistake. You sort of start with the basics, and then you start calculating, you do a lot of algebra, because finally in the end you want to have one nice cute little answer with 2 lines under. Why? Nobody has asked you to do that. Or have they? If they asked you, okay, then you have no choice, then you have to do all the algebra. But if nobody has asked you, then why do it? Why do all this tedious algebra if you don't have to? Like this one. Here I now have 2 differential equations, and I have an equation here as well. So actually this A has to be inserted here, and then you have to sort of clean it up. But I haven't asked you to do that, nor has MATLAB. If you want to do the programming here, well, leave it like this. You don't have to do this algebra. Calculate A first and just use it. MATLAB has no problem with fighting with what you call here a DAE system. It's differential and algebraic equations in the same time. So in the same function, you just calculate this coefficient A first, this parameter, and use it in the expression later on. No problem. So don't do all the algebra unless you have to. This will be typically the case, as you saw previously, with these virtual elements. That can be a lot of algebra. Very boring. But why do the algebra unless you have to? Of course, it might be nice in the end to just have the state equations only and nothing else. But it's really not a big problem. So just leave it like that unless you are really eager to get the equations neat and clean. No problem. Okay. Any questions? Then we will have more examples tomorrow. So then we stop here.